Hi guys, in this video we're going to be talking about free body diagrams, otherwise known as force diagrams. In order to start looking at force diagrams, let's examine this situation. We have a table which is sat on the ground, and on top of the table we have a box. Now we know from Newton's third law that forces come in pairs, so let's start looking at some of the force pairs that are involved in this scenario. Here we see that the Earth is pulling down on the box, but the box is also pulling up on the Earth. We also have that the table is pulling up on the Earth and the Earth is pulling down on the table. We then add two more forces that represent the box pushing down on the table and the table pushing up on the box. And finally, we add two forces that show that the table is pushing down on the Earth and the Earth is pushing back up on the table. It's pretty easy to see that even simple situations like this lead to a whole bunch of interacting forces. What we normally are interested in, though, is what will be the motion of a single object. And to know that, we need to know about all of the forces on the object. Let's imagine then that we're only interested in the box on the table, and we're going to strip away everything else and show only those forces that are acting upon the box. We don't care about the other blue arrows where the box is acting on the table or acting on the Earth. What we get then is this diagram. The box has two forces acting upon it. One, acting downwards, is the force of gravity. This is sometimes labelled as W for weight, and is equal to the mass of the object times the acceleration due to gravity. The force pushing the box up is a reaction to the box being pulled into the table, and is known as the normal force. In this case, we know that both of those forces are equal in magnitude because the box is stationary, and according to Newton's first law, the box will only remain at rest if all of the forces are balanced. What we have drawn here on the right is the free body diagram for the box. Anytime you draw an object and show all of the forces acting upon it, you have drawn a force diagram or free body diagram. Let's look at our second example then. We have a box sitting on the ground, and this box is going to be pulled by a rope acting at an angle of theta from the horizontal. So we have a force F being applied in that direction along the rope. We have the weight of the box down, and we have the normal force of the ground on the box acting up. Now, at this point, I'd like you to pause the video and ask yourself the question, why have I drawn the normal force so small? In the previous example, I said that it was equal in magnitude to the weight of the box. And yet in this case, I'm indicating that it will in fact actually be much smaller. Why is that? If you said it's because the force on the rope was partially pulling the box up off the ground, you would be right. If I was to pull up equal to the weight of the box, I could have it hover just touching the ground but not actually pressing down into it. As I pull it up more and more, I actually reduce the amount of interaction that happens between the box and the ground. So what we've got here is a vertical component of that force on the rope that is acting to support its weight. If we wrote an equation representing all of the force components vertically, we'd have the following. The normal force plus the vertical component of our force F is equal to the negative of the weight force. In this way, all of our vertical vectors add up to 0, which makes sense because the box isn't going to move vertically. It's neither going to drop nor rise. Horizontally, on the other hand, we have only one force. The force of the rope acting horizontally is going to act upon the box without any other force countering it. In this way, the box will actually accelerate forwards and it will move across the ground at an increasing speed. We say that the total force on the box is F net, once we've added all of the different force vectors together. In this example, we've got quite a lot going on. We've got two masses with a rope between them, which are then connected by two other ropes to a ceiling or roof. What we're imagining is that this situation is static. All of the forces are balanced so that the objects are not moving at all. As part of this arrangement, we have tension in each of the ropes. Now, the thing about tension in a rope is it acts at all points in both directions. You have each part of the rope pulling the parts next to it and being pulled by them, to the point that the tension in rope 1, T1, is going to be pulling down on the roof at that angle with that amount of force, and will be pulling up on the object at that angle with the same amount of force. In the same way, T2 can be considered to be acting to the right on M1 and to the left on M2. In problems like this, you're asked to solve for what the tension in each of the ropes is. And you do this by separating it into two free body diagrams. If we consider our M1, then we have its weight equal to M1 times G acting down, the tension in the second rope acting to the right, and the tension in the first rope acting up at an angle of theta from the horizontal. For the second mass then, we have T2 acting to the left, its weight equal to M2G acting down, and T3 acting at an angle of phi from the horizontal. The trick to answering such a problem is to remember that we require each of the objects to be stationary, at rest, which means all of the forces must balance. For the second object, we can write equations like T3 cos phi must be equal to negative T2, so that it cancels out the horizontal force. And in the vertical direction, T3 sin phi must equal the negative of the weight, negative M2G. And we can do the same for the first object as well. T1 cos theta equals negative T2, and T1 sin theta equals negative M1G. Knowing theta and the mass of the object and the acceleration of gravity means that we could work out what the size of T1 is, and then go to the first equation, and knowing T1 and theta, we could work out what T2 is. And then we could do the same for the other side and work out T3, and also again work out T2 and make sure that our working is accurate. There's one final thing to say about tensional forces, and that's if we've got something like a pulley. If we have a mass M being hung from a rope that extends over a pulley, then the force pulling down, F, must be equal to the weight. The rope has redirected the force. So in terms of magnitude of the forces, the weight of the object, mg, is equal to the tension in the rope, which is equal to the force pulling down on the other end of the rope. So while it looks like the two forces that are being applied, the weight of the object and the force, are acting in the same direction, it still works out that all of the forces at any particular point balance. Because if we consider just the mass, then the weight is acting down and the tension of the rope at that point is acting up. If we consider the force, then I'm holding the end of the rope with a force F, and tension is pulling back against me at that point upwards. It's just that because the tension in the rope acts all the way along the rope, it actually follows the contour of it. And so ropes and pulleys can be used to redirect forces, and we'll see that in the coming weeks.